Well, it's really nice when only two things are changing, but that doesn't always happen. Sometimes three things change, or even four. So the combined gas law puts Boyle's law and Charles' law together for situations where the pressure, the volume, and the temperature are changing, and only the amount of gas is staying the same. So this is a more realistic sort of situation. So this is the combined gas law. And you can see that Boyle's law and Charles' law are both in here, right? Here's Boyle's law, right there. And then Charles' law is just looking at this part. So if you took the combined gas law and the pressure wasn't changing, the pressures would cancel out and leave you with Charles' law. So that's the combined gas law. We're going to solve problems with this in the same approach. Our table's just going to have an extra column. And there tends to be more words in the question. You do need to know the formulas, the equations. So you can memorize them, or I will show you how to create them out of the ideal gas law. And we'll get to that. A sample of gas has an initial volume of 158 milliliters at a pressure of 735 millimeters of mercury and a temperature of 34 degrees Celsius. If the gas is compressed to a volume of 108 milliliters and heated to a temperature of 85 degrees Celsius, what is the final pressure in millimeters of mercury? Purple, because aliens don't wear hats, right? It's like, what the heck? This is a whole bunch of numbers. We're just going to pull the numbers out and stick them in an equation. So read through it to make sure there's nothing crazy like, those trick questions on exams that teachers sometimes do, where the first one is read the exam before answering any questions, and then at the bottom it says sign your name and turn it in. Yeah, you should always read through the whole thing. So we're going to go through and we're going to find the numbers and we're going to put them in a table, and then we'll know what to do with them. First number, 158 milliliters. Okay, so I'll write that down. 158 milliliters. That's in a column, and that's a volume, so I'm going to call this column B. 158 milliliters at a pressure of, so those go together, 735 millimeters of mercury. That's the pressure. And the temperature of 34 degrees Celsius. What do we have to do that? Put it in Kelvin. Let's do it right away before we forget. 34 plus 273. This is 307 Kelvin. Blah, blah, blah. If it's compressed, so there's the wording about something changing. Volume of 108. Okay, so put that in the volume, 108 milliliters. And heated to a temperature of, so skip the pressure, 85 degrees Celsius. Got to convert that to Kelvin, so 85 plus 273, 358. What's the pressure? Oh, well, that's convenient. We have a blank in the pressure column. Let's call that pressure tube. Okay. So now we see that we have volume, pressure, and temperature changing. We can't use Boyle's law or Charles' law. We need to use the combined law. The combined law is P1 V1 over T1 equals P2 V2 over T2. Fractions, cross multiply. P1 V1 T2 equals T1 P2 V2. These always make me think of R2D2. Okay, so I cross multiplied. This top times that bottom equals this bottom times that top. And I'm looking for P2, so I divide by the other things that are next to it. I want the T1 to disappear. I want the V2 to disappear. If I do it to that side, I have to do it to the other side. Got to be fair. So that looks like a big old mess, doesn't it? Copy it down carefully. P2 equals P1 V1 T2 divided by T1 V2. And then compare it and make sure you didn't switch something. Now we just pull the numbers out of the table. Pressure 1, 735 millimeters of mercury. Volume 1, 158 milliliters. Temperature 2, 358 Kelvin. Temperature 1, 307 Kelvin. And volume 2, 108 milliliters. So look at the units. The kelvins cancel, the milliliters cancel. I'm left with a pressure unit, so that's a good sign. When you are doing this, be careful, because this times this times this divided by this times this is going to get you the wrong number if you press it in your calculator that way. If you want to multiply these, where's my pointer? If you want to multiply those when you're dividing, you have to put parentheses around them. So get your calculator out if you don't already have it, and make sure that you can get the same answer here. 735 times 158 times 358. What I do is I go divide by 307 and divide by 108. 1253.9. Everything's 3 sig figs. And the unit is millimeters of mercury. Did you get that number? Okay. If you got a number that's much larger than that, it's because you're having this dividing issue and you accidentally multiplied by 108 instead of dividing by 108. That'll cause you problems. So I should round this to the tens place, to the nearest 10. That's not 125. It's 1,250. So 3 sig figs is going to be 1250 millimeters of mercury. Scientific notation is always awesome. 1.25 times 10 to the third millimeters of mercury. Any questions? Yeah.
Instead of doing the table, I feel more comfortable listing all of the different presses. Am I going to not using the table?
No. So the question is, if you feel more comfortable just listing them out, like making a list of, okay, P1 equals this, V1 equals this, T2 equals that, would you get docked points for not making the table? No, not at all. Just make sure that you're getting things labeled correctly. So yeah, you can definitely do that. I would not recommend just starting with this equation and putting numbers in just from the problem without labeling them in some way, because there's just so many numbers. It's just really easy to get them mixed up. Any other questions? A balloon has a volume of 3.7 liters at a pressure of 1.1 atmospheres and a temperature of 30 degrees Celsius. If the balloon is submerged in water to a depth where the pressure is 4.7 atmospheres and the temperature is 15 degrees Celsius, what will its volume be? And then the fine print, assume that any changes in pressure caused by the skin of the balloon are negligible. So, read through the problem. I'm going to make a table. If you are more comfortable just listing things, that's absolutely fine. So, volume 3.7 liters at a pressure of 1.1 atmospheres and a temperature of 30 degrees Celsius. So this is my volume, my pressure, and my temperature columns. Degrees Celsius is a no-no, so we need to convert that into Kelvin. And so that's going to be 303 Kelvin. So all of these are connected, those are all together. The balloon is submerged, and now this is the pressure, and this is the temperature. So we put those in. We got 4.7 atmospheres for the second pressure, and the temperature has gone down also 15 degrees Celsius. So we convert that to Kelvin, that's 288 Kelvin. We have one blank in our table, we'll call that V2. We're going to use the combined gas law, P1V1 over T1 equals P2V2 over T2. Here we're solving for volume 2. So cross multiply I want V2, so I'm going to divide by T1 and P2. Divide by T1 and P2. What I do when I look at this equation, I can just write down the rearranged form, because if something's in the denominator of one side of the equal sign, you can take it and just move it to the numerator on the other side. If something's on the numerator like P2, you can just pull it down here into the denominator on the other side. That is the equivalent of what we're doing here, but if it doesn't make sense to you, then it's not going to work very well. So volume 2 would equal P1V1 over T1, and then T2 on top and P2 on the bottom. So now I just plug in the values. 1.1 atmospheres for pressure 1. Volume 1 is 3.7 liters. Temperature 2 is 288 Kelvin. Divided by, it's getting sloppy, temperature 2, temperature 1. Got to look at those. 303 Kelvin. And pressure 2, 4.7 atmospheres. You should be using each number in here once. If you use one twice, you got confused. So the units work out. That's encouraging. 1.1 times 3.7 times 288. If you really like multiplying in the denominator, then after the 288, I'm going to go divide, and I'd have to use parentheses, 303 times 4.7, and then close the parentheses to make sure that my computer understands, my calculator understands what I'm telling it to do. 0.823. The unit would be liters. So my volume is 2 sig figs, the pressures are 2 sig figs, so this is going to have two significant figures. And so I've got 0.82 liters. Anybody else get that number? Thanks. Is it reasonable? Well, with the combined gas law, it can be a little more difficult to say, is it reasonable? Because sometimes the changes can oppose each other. But here the pressure went up, so that would make it go smaller, right? Volume go down. The temperature went down. Cooling a gas also makes it smaller, so definitely the volume should be smaller, and it is. Questions?